Hi everyone, welcome back. In this particular video, we're going to discuss the Wolff-Kishner reduction. Now, this reaction offers as a method for reducing a carbonyl compound. And the reaction is done over two steps. So it's a two-step process. Initially, the carbonyl compound is reacted with hydrazine. Okay, this molecule is hydrazine, which converts the carbonyl compound into what's called a hydrazone. So the resulting product is called a hydrazone. And then the hydrazone is reacted with a base under aqueous conditions with heat to give an alkane. So now an alkane, if there are no other functional groups in the molecule. So we're focusing on the carbonyl group here. So essentially what you notice is you had the carbonyl carbon here with the double bonded oxygen, and in your product, you have two hydrogens here. So it's an overall reduction because we have removed the oxygen atom here and we've added hydrogens. So as a quick example for this, so let's assume that if we had a carbonyl compound like this, okay, that's a ketone. So if we do a reaction where this is first treated with H plus and into H4, the hydrazine, okay, and second, you treat it with base. What would happen is this C double bond group would be lost and we will get the product. So your ketone would be converted into an alkane here. Now, the mechanism of formation of the hydrazone, this, if you look at the connectivity here, this is very similar to that of the imine. Okay, so if you know the mechanism of an imine synthesis or the imine formation, you can write a mechanism for the formation of a hydrazone product here. What we're going to do next is we're going to look at the mechanism of this reduction. How does the hydrazone convert into the alkane product? We're going to look at that. So I hope this example gives you like an idea of what is going on. It's a very simple reaction. So I'm not going to like elaborate more or like give more examples here, but let's go look at the mechanism because that is what's interesting here. So in terms of the mechanism, and we are looking at the mechanism for this second step, which is the actual reduction of the hydrazone into the alkane. So under those conditions, notice how the conditions are basic. So the hydrazone as you can imagine under these conditions, a likely step that can happen is the deprotonation of the hydrazone because these hydrogens are acidic in nature because they're converted to an electronegative element. So the base hydroxide, it can deprotonate one of these hydrogens. Now, when that happens, this lone pair would go to the nitrogen. So let me write that product out, onto the intermediate out, and then we will see what happens to that intermediate. So we get NH, and at this point we have two lone pairs on the nitrogen, one lone pair on this nitrogen, and we have a negative charge. Plus we get water here. Okay, that intermediate can now do resonance. Okay, those electron pairs, they are basically allelic in nature. So those electron pairs can be pushed here, which would open up this pi bond and put a negative charge on that carbon. So the next resonance form that we'll get would look like this. There's a double bond with the nitrogen, there is a hydrogen, there's one lone pair here, and there is a negative charge on that carbon. Okay, so that's just resonance. And this carbon here can now get protonated because you have water around. That's your solvent. So that negative charge can pick up a proton. Electrons would go to the oxygen. And notice how that's generating more base hydroxide there. Okay. So at the end of this, we're going to get R, N, double bond, N, H, lone pair, and we've added one hydrogen to that carbon. So our reduction is halfway through. We've added one hydrogen to that carbon, and we've converted the double bond into a single bond now. Now we are also generating more hydroxide here. Okay. And since the reaction is overall under basic conditions, what can happen next is the hydroxide can go and deprotonate this intermediate. The electrons would go to that nitrogen atom. So again, because that hydrogen is still acidic because it's connected to the nitrogen, which is an electronegative element. And as that happens, we're going to get this new intermediate where we have the nitrogen double bonded to the other nitrogen, lone pair, negative charge. There is one hydrogen here, and plus we've got water. And now this ion that we made, this can actually liberate nitrogen gas. So if one of those lone pairs came down, when it comes down to the space between the two nitrogen atoms, we're going to make a nitrogen-nitrogen triple bond. That's what nitrogen gas is. Simultaneously, the single bond here, it breaks. And so it would give you a carbanion. So there's that hydrogen, there's a negative charge on that carbon. And plus, we've made nitrogen triple bond nitrogen, which is nitrogen gas. So the loss of this nitrogen gas, which is like a small molecule, it makes this whole process irreversible after this step. Now, before this point, notice how we're doing acid-base reaction. So this must be reversible. There's another acid-base reaction here, so that must be reversible. And there's acid-base here, so this should also be a reversible step. But once the nitrogen gas is lost, okay, this just escapes from the system. Once that is lost, this reverse and the reaction becomes technically irreversible at that step. Okay, and so then this carbanion that's generated, it can go ahead and get a proton from water, which is our solvent, and give us the alkane product, where now we've got two hydrogens here and additionally hydroxide back. So overall, this process should be catalytic and hydroxide because you're not really using up the hydroxide. You're getting it back at the end of the reaction. Okay, so it should just be catalytic and hydroxide. But that's the mechanism of the Wolff-Kishner reduction, specifically the second step of the reaction, where the hydrazone is converted into the alkane. And overall, the Wolff-Kishner reduction is a two-step process: an initial hydrazone formation and then the reduction to the alkane. I hope all of you find this video helpful. Bye.